All right, so we're getting ready to start the last session here at DeepMath. Next is a contributed talk from Maria Refinetti, and she is a PhD student at École Normale Supérieure. I promise I can speak at some point. Will be telling us about the dynamics of feature learning with shallow nonlinear autoencoders. So it is all yours. Take it away.
Thank you, and thanks for the organizers for having me. I'm really happy to present this new work with done in collaboration with Sebastian Goth from the CISA in Trieste. And this works, as you said, deals with the dynamics of feature learnings with shallow nonlinear autoencoders. So as most of you probably know, a key question in the field of neural networks is how these networks learn a good representation of their data. However, despite this fact, feature learning is still very poorly understood. Autoencoders, which are an unsupervised learning architecture trained to reproduce their inputs, provide a very good playground to study this feature learning procedure. In particular, linear autoencoders have been much studied, and it has been known for some times now that they just do principal component analysis of their data. However, what is less clear is how do these linear autoencoders learn good representations? The dynamics of linear AE has been studied in recent years from various perspectives, from that of the loss landscape, of the convergence of the gradient, or on how to recover the exact principal components. However, there is something missing here, which is that it is believed that feature detection in neural networks crucially relies on the non-linearities, which are not present in a linear autoencoder. And therefore, the question we're aiming to answer in this paper is, what can we say about non-linear autoencoders? And our contributions here will be to derive a closed set of equations which track the dynamics of training of a nonlinear shallow autoencoders with order 1 hidden nodes. We'll show how to derive an algorithm that allows us to recover exactly the eigenvectors. We'll also argue that it is crucial to untie the weights of these autoencoders, to add a bias when training a ReLU autoencoders, and how these two things relate to their overall performances. Finally, we'll show how our results apply to real data sets and are able to describe training also on benchmark data sets such as Cypher10 or FashionMNIST. So let me give you a bit more details on the setup. We are giving a shallow autoencoders that is trained to reproduce its input that has order 1 hidden nodes and a nonlinearity in the middle. We will train it on a data set of n inputs, and we will train it to minimize its reconstruction error. Then we'll evaluate it through the population reconstruction loss. In particular, we will choose the high dimensional limit, and we'll train our network through online or one-pass SGD, in which each sample is seen only once by the network. I will add that we derive our equations and our results on Gaussian inputs that allow us to have very precise control over the spectrum of their covariance matrix, and therefore to untangle the different contributions from the results we derive. The kind of technique we'll use has a long history in the context of supervised learning, from IID inputs in the 90s until more recently on data with non-trivial input-input correlation. And I want to stress again that although we derive our equations and our results on synthetic data sets, we'll then show that the theory actually also describes training on real data sets, and that most of the results carry over. Now, to show a bit our strength, so what are we trying to compute, and what do these equations tell us? So our equations have as a goal to compute the prediction mean squared error at all times, which ultimately tells us all about the performance of the network. When we write this error, we see that there is a high dimensional expectation over the inputs that appears. However, by expanding it, we notice that the inputs only appear through a low-dimensional projection on the weights of the network, and we'll call these projections the local fields. Hence, we can replace the high-dimensional inputs, the high-dimensional expectation over the inputs, with a low-dimensional expectation over the local fields. And now we must recall that we're working with Gaussian inputs, and therefore these local fields are jointly Gaussian, which means that the PMSE is entirely determined by their first two moments. Hence, by deriving some equations for these order parameters, or these overlaps as we call them, we can find a closed set of ordinary differential equations tracking the population mean squared error at all times. Now, by testing these equations on a synthetic data set, so in this case, I'll choose a synthetic data set in which the covariance matrix of the input is made up of a bulk of eigenvalues and some spikes. So wait, I think, okay, well, which is made of a bulk of eigenvalues and some spikes. And what we find in deriving the equations is that we have a separation between the evolution of the bulk mode and the evolution of the spikes mode. And we find different set of equations for each. Something else of interest is that if we look more carefully at the equations for the spike modes, we see that their learning rate is rescaled by the corresponding eigenvalue. What this means is that we expect each mode to be learned sequentially from the highest eigenvalue ones to the lowest eigenvalue. A bit as is seen is in the sequential learning in other studies. And indeed, when we integrate these equations and we compare them to simulation, we see that indeed there is a very good agreement between theory and experiment. We check that in the nonlinear autoencoder also only recovers PCA of order K. And we can also verify that the sequential learning of different order modes occurs. And this can be seen through these plateaus that we see in the generalization error. So let us analyze in more detail what is the representation learned by the network. By plotting the weights of the encoder, what we can see is that it doesn't recover the exact eigenvectors, but a rotation of this. So the way we see this is that I chose my data set in such a way that the eigenvectors are sinusoidal. So there are these black lines, which you can see in the plot. And so by plotting the weights at final time, I can see whether they recover it or not. And so what I want to understand is how to learn the exact principal component and not just a rotation of it, and how the network recovers the linear performance despite the nonlinearity in the hidden layer. So let us address the first question. In the context of linear autoencoders, it is known that the weights only converge to a linear combination of the principal components due to the rotational symmetry in the SGD step. And there are various ways to recover the exact eigenvectors which have been proposed. Some leveraging on alternative optimization algorithms such as Sanger rules or Ojas rules, and others that explicitly break the rotational symmetries in the weights update. We have chosen to go a bit more, to do some analogies with Sanger's rule, which we can see breaks the rotational symmetry in the update of the weights by summing only over subsets of weights. And when we compare this to the BP step of a nonlinear autoencoder, we see that we can do a similar thing by truncating the sum only to a subset of nodes, and that this will allow us to break this rotational symmetry in the SGD step, and therefore, hopefully, to converge to the exact eigenvectors. Indeed, by using such a truncated algorithm, we can check that we have no loss in performance, and that the network, the weights of the network, indeed converges to the exact eigenvectors, which is what we want. Now, another question that we wanted to address is how does the network recover the PCA performances? And a way to study this is to study the long time dynamics of the autoencoders, which can be studied thanks to the equations we derive. Now, let us be a bit inventive. So we have a theoretical descriptions and a theoretical equations, and we expect the weights, as we have seen at long times, to recover configuration in which they are proportional to the eigenvectors. Therefore, what we choose is to make an ansatz on the form of these weights. And this ansatz, you can see, is a proportionality constant times the eigenvectors of the covariance matrix. This ansatz results in a diagonal ansatz for the order parameters, which we can plug into the theoretical equations we derived. This allows us to find a simplified set of ODEs only for the proportionality constants. And by integrating these ODEs, well, we can first observe that they capture very well the dynamics of a neural network, of an autoencoder trained from random initial conditions, which suggests that the weights aligned very early on in training with the principal components. And then we can also see a learning in two phases. First, the weights of the autoencoder recover the principal component space, and then they adjust the norm of the weights in order to decay their error. Now, looking a bit more closely at these equations, we see a result which is actually stronger, which is that the decoder's weight shrink while, the encoder's weight shrink while the decoder's weight grow as a power law in time. And so we want to understand what is happening. How come we have this growing and shrinking of the respective weights? And we can understand this by reminding ourselves that for a sigmoidal activation function, it is linear around the origin. Therefore, if the encoder's weight are shrinking, the nonlinearity is actually evaluated around its linear regime. And so that ultimately the autoencoder is only doing a linear transformation of the input. And then the decoder's weight must grow in order to ensure that the norm of the reconstruction is similar to the norm of the input. So this makes us understand that the way that the neural network, that an autoencoder recovers the linear performance is by shrinking its encoder's weight and making the decoder's weight grow. And so that therefore it just makes a linear transformation of the inputs. But this has catastrophic impact on the training of tight weight autoencoder and seems to suggest that, well, these tight weight autoencoders in which the encoder's weight are constrained to be equal to the decoder's weight will not be able to learn. And indeed, when we check this prediction that comes from our equations, we can really see that this is the case. The tight weight autoencoder completely fails to learn, while as soon as we untie the weights, we have learning onto the PCA direction. Now, this suggests that something different must be going on with a ReLU autoencoder, because the linear regime of ReLU is the positive real axis. And therefore, it suggests that in order to achieve good performance, we need to train the biases. Indeed, when we make simulations, we can check that if we don't train the bias, there is a large gap between the autoencoder's performance and PCA. When we do train the bias, it improves performance considerably. And we can also see that the asymptotic error is given by the PCA error plus some residual due to the fact that we're adding the bias. A last check is the fact that if we start a network with random initial condition for the bias, in which some are positive and some are negatives, at the end of training, they'll all be large and positive, really suggesting that the network is making these biases grow in order to be always evaluating the nonlinearity in its linear region, and therefore just to perform a linear transformation of the inputs. Now, the last but not least at all, and most importantly, we want to look at how much these results on synthetic dataset extend to finite realistic data, which are very different to the synthetic model to the extent that, well, they're finite, they have finite number of inputs. The inputs are non-Gaussian, and also finite dimensional. So the first check is that a tight weight autoencoder indeed cannot learn. And these are simulations made on Cipher 10. Then we also check that a ReLU autoencoder requires the bias to achieve good performance. Finally, we can also see that the learning dynamics slightly slows down at intermediary ranks, showing that the modes are learned sequentially during training. We do no better than PCA. And most importantly, when we run our equations, we can see that they capture very well the training dynamics on Cipher 10. And so that we have a very good agreement between theory and practice. So this is it. Thank you very much for your attention.
Thank you so much. I'd like to open up for questions, and maybe while people are putting that together, I had one question. So this is really interesting in terms of the fact that it all kind of comes back to a linear autoencoder for this architecture. Is there a sense that when you look at deeper architectures that you have the exact same, like, I guess, reversion to the linear case?
So we yet haven't tried this because we're planning to try deeper architectures. However, it is possible because there is the result that actually argues that nonlinear autoencoders just do PCA, actually argues that if you do not add a nonlinearity in the output, well, then the best thing you can do is actually PCA of whatever comes in the last layer. So I wouldn't be so surprised if by adding layers, in the end, you would see a similar thing occurring. So all the weights in the encoder shrinking with all the weights in the decoders growing.
Interesting. So that's okay. Thank you. That's a lot to think about. Do we have any other questions from the audience or from the panelists? Okay, well, in that case, thank you very much for joining us and presenting, and we appreciate your sharing your work with us.
Thank you. Thank you for inviting me.
Oh, wait, sorry, we have one more question. Sorry to drag you back. Cameron Harris asked, do you think the linearity is mostly due to width being small or depth?
I think it's more. I think it's more due to the width being small, but let's say that there are some works also looking at autoencoders in the mean field limit, so in which we take the hidden layer size going to infinity, and they don't seem to see this kind of linear. Let's say that they always need to put some constraint in order not just to reproduce your input, in a sense, not to just do a linear transformation as well of your inputs. So I would say that it's mostly due to depth, probably.
Thank you. All right, well, let's thank you one more time. And
thank you.
Yeah. So next we have Kamalika, can you share your screen?
Yes, just give me a minute.
Take your time.
Share screen, there you go. Let me try to play. Sorry, give me 1 second. Yes.
Oh.
Yeah, do you guys see it?
Yes, we can see.
Okay.
Great, and so I guess let's get started. So for our very last speaker for the conference, we are excited to have Dr. Kamalika Chaudhuri, and coming to us from University of California at San Diego. She received a Bachelor's of Technology degree of Computer Science and Engineering from the Indian Institute of Technology, Kanpur. PhD in Computer Science from UC Berkeley. Has been a postdoc at the Information Theory and Application Center at UC San Diego, and is now in the Computer Science the CSE department at UCSD as an assistant professor, or associate professor now, or co-professor. Which one?
Well, associate, I was just going to say I was very happy to have gotten my tenure. So.
I was going to say, like, it seemed, I think this is going in chronological order as I put it. So I was like, this seems wrong. You're definitely more than that. And,
that's the biggest faux pas. You can't take tenure away from somebody.
I'm so sorry. I'm so sorry.
I'm just joking.
And so amongst many other, Dr. Chaudhuri has the NSF Career Award, a Hellman Faculty Fellowship, and is a forefront in the research of design analysis of ML algorithms and their applications, in particular, clustering, online learning, and privacy preserving ML. And so thank you very much for joining us. And again, please feel free to hold that against me for the rest of my life. We're excited to have you.
Thank you, Adam. That was a really nice introduction. So I guess I would start off my talk by saying that I don't really directly work on deep learning. So what I work on, and I'll tell you a little bit about this, is on what I would broadly call reliable machine learning or trustworthy machine learning. But what I'll talk about today is, as you will see, some of my work does intersect with deep learning. And, what I'll talk about today is a couple of places where this happens. And perhaps as a result, there are some interesting things we can say about both, this kind of reliable and trustworthy machine learning as well as deep learning. So that's going to be what I'm going to talk about today. So what do I mean by reliable learning? So if you open your first textbook on machine learning, this is what you see, right? So this is the textbook machine learning, where you have a bunch of training data, and then that goes into some, magic training algorithm, outcomes a classifier, and then that classifier is evaluated on test data, right? And here, what you assume, this is underlying assumption that this training data is drawn IID from some underlying data distribution, and then the test data also comes from the same distribution. And then if you want to get, high accuracy on your, then if you want to get a good classifier, well, what you are asking for is high accuracy on this test data, right? So that's kind of the definition of good classifier, and that's, what we are trying to achieve, right? So in most kind of textbook machine learning situations. The reality, however, is a lot more complicated, right? So when you try to deploy a lot of these classifiers in practice, maybe, beyond just recommending ads, when you try to deploy these classifiers in a lot of real applications, what happens is that there are many issues that come to the forefront. So for example, the classifiers need to be robust because your sensors might break when you are trying to collect data. Your classifiers need to be robust, not to just, the kinds of images that you have seen, but maybe slightly different, images. Then very often in training data, there is sample selection bias. So for example, maybe training data, just because of the way you collected your training data, maybe certain kinds of examples are not collected as much, or they're not as well represented. So that would be an example of sample selection bias. Then there's a lot of sensitive data around that a lot of machine learning is now done on. So there's privacy, there's interpretability, and a lot of other issues. And what my group has been doing for the last, I think, several years is we look at the foundations of these kinds of issues, right? So we are, we mostly do theory. So we do a mix of theory and a bit of, trying things out. And what we try to do is to understand the foundations of these aspects of these things. Okay. And today what we'll talk about a little bit are, kind of two threads in our work where we intersect deep learning because, it's a conference on the mathematics of deep learning. And the two aspects that I will talk about, so one is robustness or adversarial robustness, and the other is overfitting. Okay. So most of you have, I'm sure, seen adversarial examples where, if you haven't, here is kind of the most typical example where what happens is you see, you see this image of the panda on the left. And what you do is you add 0.007 times the image in the middle, right? And that looks like Gaussian noise, and it's 0.007, so you're not really adding a lot of stuff. And what comes out is the image on the right. To me, and I'm sure to most human beings, it looks like a panda. But many state-of-the-art neural networks are completely convinced that this is a given, right? They're convinced that it's a given with very high probability, right? So what is happening over here is that there are these small perturbations to legitimate test inputs, right? So this is kind of a legitimate test input. I mean, normally it would have even been classified as a panda, which causes misclassification. And then there are cases where this could be dangerous. So for example, if you, imagine instead of having an animal classifier, if you had a street sign classifier, and if your street sign classifier made mistakes, then, and if you were using it in your car, then you would have a serious problem, right? So what is known about adversarial examples? Well, there's a very large number of attacks. There are a handful of defenses, but even now there isn't a lot of understanding on why they happen. And what our work has looked at over the last, we've had a series of papers on this since 2018. And over the last several years, what we have been looking at is why do these things happen, right? So why do we have adversarial examples? Okay, so why would we have adversarial examples? Well, if you turn back to learning theory to try to understand why they might happen, there might be three explanations, right? Three plausible explanations. One explanation is that the data distributions overlap. So, the pandas are very close together in space from gibbons, and so it's really, you can't really separate them from each other really, in a large margin sense, right? You can't really separate them from each other robustly. The second option is that even though the pandas are far apart from gibbons, what is happening is that we don't have enough samples to to figure this out somehow, right? The samples that we have, they're very sparse, and there's not enough, so we can't really figure this out. And the third possibility is that even though, we have the data distributions don't overlap, maybe we are doing okay in terms of samples. The third possibility is that the algorithms that we are largely using to find these kinds of classifiers, these algorithms are not very good, right? So maybe we have bad algorithms. And what I will do is I will give you the answer ahead of time. And the answer is mostly it's number three. Mostly the algorithms are not that great. Okay, so let me start out with some background. So we are looking at classification problems where what happens is we have xi, yi pairs. Xi's are the feature vectors and yi's are discrete labels. And what we are trying to do is we are trying to find the prediction rule in a class to predict the y's from the x's. Okay. And, and this is the statistical learning framework that I had talked about earlier, where training and test data are drawn from the same underlying distribution. They're drawn independently. And the goal is to find the classifier F to maximize the accuracy, right? And what is the accuracy? Well, the accuracy is the fraction of times your F of X agrees with Y, right? The fraction of times you can predict the correct labels for, input label pairs that are drawn from this distribution. Okay. So how do we measure robustness over here? Well, let's look at that, right? Suppose you have a classifier F. This classifier will be robust with radius S at a particular point X if for a distance function D, the distance between X and X prime greater than or equal to S implies that F of X equal to F of X prime, right? So what does this mean? What it means is that F predicts the same label in a ball of radius r around X, okay? And why is this interesting? Well, the reason why this is interesting is that this implies that there are no adversarial examples around X, okay? So what kind of metrics do we look at when we look at, when we look at adversarial examples? Well, the metrics that we look at, so we care about two metrics. So of course, there is the clean accuracy, but we also care about adversarial accuracy, which is the accuracy against adversarial examples at a particular radius S, right? So we want our classifier to, classify legitimate inputs correctly, but we also want them, for the given that, for this transform panda that you saw, we want, so we want those to be classified as the pandas as well, okay? Okay, so how do we think of robustness? So this is, general robustness. How do we think of robustness in neural networks? So for the purpose of our work, what we will do is we will think of the following abstraction. So we'll think that the neural network computes a function f of x. So, it's a continuous function, maybe it's a very complicated continuous function. And here what we'll do is we will just look at binary classification just to keep our lives simple. I mean, all of these extend to multi-class as well, but with a lot more notation. So for now, we'll just keep our life simple, and we'll, so we will think about binary classification. And then what we will do is we'll assume that the classifier, takes this function f of x and then just outputs its sign, and that is the label, right? So it's a plus minus one label, which would be the sign of this f of x, okay? So how do we get robustness here? So we are going to assume that the robustness comes from local smoothness, right? So if you have a function f, which is locally Lipschitz around a point x, and if f of x is bound, is away from 0, then f is robust at x, right? So this makes a lot of sense, because what this means is that if you have, our test input x, f of x is quite a bit far from 0, and f of x is smooth around x. So to get to 0 or to cross over from 0 to change the label, you will have to go quite a bit of a distance, right? So it's kind of a trivial theorem, but it's kind of a trivial idea, but this is what it means, okay? So what is known for neural networks? Well, again, there's a large number of attacks, a few good defenses. However, all the defenses that we have generally show a robustness versus accuracy trade-off. And today what we'll talk about is whether this trade-off is inevitable, right? In the sense that, do we have to have this trade-off? And what I will try to convince you is that this does not need to happen in principle, at least for real data, right? At least in principle, this shouldn't happen, okay? Okay, so before I get to this, let me start out with a particular notion, which is the notion of R separation, okay? So we say that the data distribution is R separated if for any pair of labeled points, x, y, and x prime, y prime, drawn from the distribution, if y is not equal to y prime, then the distance between x and x prime is at least twice r, right? So what this means is that any two points with different labels are at least distance 2r apart. It's kind of like this distribution in the picture, right? I mean, the label points might have multiple clusters, might be very complicated, but if you have any two points that are at least distance twice r apart, that have different labels, then they have to be at least distance twice r apart. Okay, so this is R separation. So why is R separation interesting? The reason why R separation is interesting is because if your data is if your data distribution is R separated, then you can get robust, highly robust and accurate classifiers, right? And, I mean, this is really not a very complicated theorem, but, it's more of an observation, is that if your data distribution is R separated, then you can get something which has accuracy 1, robustness radius R, and that comes from rounding a locally smooth function, right? So you can get this kind of a classifier, not only can you get a perfectly accurate and robust classifier, you can even get it from rounding a smooth function, okay? So, well, okay, so that is interesting, but what happens with real data, right? Turns out real data is very much R separated. So what I have over here is we did a bunch of measurements, right? So we have these 4 data sets, MNIST, CIFAR-10, SVHN, and restricted ImageNet. So we did a bunch of measurements where we looked at how separated they are, right? The different classes are. So here our separation is the minimum distance between any 2 points in different classes. So I think this is the training, but I mean, you get very similar results for test training as well, but minimum distance between any 2 points in different classes. And the third column over here, the S, is the typical robustness radius that people use in this kind of adversarial examples experiment. So for MNIST, the typical S is something like 0.1, but the separation, right? So if your separation was 0.2, then there would exist a good classifier, but the separation is something like 0.74, right? So it's orders of magnitude bigger. Similarly, for CIFAR-10, typical S is something like 0.03. The separation is something like 0.21. And this is by the way, this is in the L infinity metric, which is the most common metric that people use for these experiments. But, these results carry over also for L2 and L1. So we have, we repeated them for L2 and L1, and, the same trend carries over. Okay, so you can see that there's an asterisk next to SVHN and restricted ImageNet. So restricted ImageNet, by the way, is a subset of ImageNet, which is used for adversarial example experiments. So, it was... it's used for adversarial example experiments. So you can see there's an asterisk. So in both cases, what happens is SVHN has a pair of images which look exactly the same but have different labels. So I think this was probably a labeling mistake, but it has, I think, 1 or 2 maybe pairs of such inputs. So we removed those 2 inputs because otherwise the separation would have been 0. And restricted ImageNet also has, so for SVHN, we removed less than 5 inputs and 5 examples. And for restricted ImageNet also has a couple of such pairs, dogs and cats and things like that. And there we also removed, I think definitely removed less than 8 such inputs. And this is the rest, right? So real data, I mean, other than very, very few, okay, so when I say real data, I mean the kind of benchmark standard data sets that we evaluate adversarial examples on, right? These standard benchmark data sets, they are very, very much R separated, right? So, so what does this mean? This means that since they are R separated, in principle, right, if we manage to find that classifier which was perfectly robust, right, and accurate, and perfectly nicely Lipschitz and accurate, so what this means is that in principle there should not be any robustness accuracy trade-off, right? However, in practice there is one, and the real question now is what accounts for this gap. Okay, so this is kind of what we look at next. So what we did was we did an empirical study where we looked at 4 standard image data sets, 7 models, 7 different training methods, which were a mix of, you will see they're a mix of the standard robust methods and some others. And in all cases, what we did is we measured the local smoothness of the classifier, accuracy as well as adversarial accuracy. Okay, and then the question we asked was that, is local smoothness correlated with the robustness? And here is kind of a typical result. So this result is for CIFAR-10, but this is kind of the typical pattern. So I'll just talk about this. So here what you have is we have accuracy, adversarial accuracy, and Lipschitz constant. So Lipschitz constant, when this is higher, it means that your classifier is not very smooth. And if it's low, then the classifier is smooth. And what you can see is that there are 2 groups, right? So if you look at the group, and these are all methods, right, for training. So there's natural training, GR is gradient regularization, LLR is locally Lipschitz regularization. And so these are So gradient regularization and locally Lifshitz regularization, what they're trying to do is they're trying to regularize the classifiers to be robust. And then there are these methods which are RST, I think robust self-training, adversarial training, and traits. These are more standard robust classification methods. Again, they are trying to also get robustness by, by doing some kind of, robust training, right? And what you see over there is there are, these two groups emerge. So the first group is kind of the red group, where what happens is that the adversarial accuracy is really low, the accuracy is pretty high, and the classifiers are not that smooth. Right? And then there's the gray group. So here actually for Cypher 10, this gradient regularization is a bit of an outlier, possibly because we had a really hard time getting it to converge. But that's kind of the general pattern. Then the second group is the gray group, where what happens is the adversarial accuracy is relatively high. The accuracy is not that great compared with the accuracy of the first of the red group. And the Lifshitz constant is really low, which means that these classifiers are really smooth, right? And so you have a group which is less smooth, more accurate, versus a group that is more smooth and less accurate, okay? And then if you look a little bit more closely, what you see is that the first group of classifiers has really high generalization gap, right? So the generalization gap between training and test accuracy, as well as training adversarial accuracy and test adversarial accuracy, that tends to be really low for the first group, whereas the latter tends to be really high for the second group. Sorry. So this indicates that, there may be some problems over here with generalization. And then we tried to look around a little bit. We tried a few different things. So for example, one of the things that is known to promote generalization in deep learning is dropout. So we tried doing dropout. And what we found was that the generalization gap improved a little bit, but not a lot, right? So with dropout, what we found, so this is, these are kind of the results. The numbers in parentheses are the numbers before dropout, and then the other numbers are the numbers with dropout. So we found that the generalization gap improved a little bit, but not a lot, okay? So in summary, what we found was that the smoother methods such as trades, RST, and adversarial training, so these were more robust, right? So they were really smooth and they were more robust. And the less smooth methods were less robust. But what we also found is that the smoother methods had a much larger generalization gap, right? And, if you think about it, this is in fact in direct contrast to what we get for, things like support vector machines, right? For support vector machines, if you have lower norm, then you have better generalization, and lower norm, corresponds to smoother functions, right? Like if your classifier vector has a lower norm, then that corresponds to a smoother function. And that has better generalization. But here what is happening is the smoother functions are having worse generalization. And dropout, does reduce the generalization gap a little, but not by a lot. I mean, it goes nowhere near to solving the problems, right? So what is happening over here? So coming back to our adversarial example thing that we started out with. So what is happening over here is that real data does remain R separated. Robust and accurate neural networks do exist. However, the current algorithms don't really find them, possibly because these robust training algorithms don't generalize well enough. And so what we need in this area is we need better methods for adversarial generalization in neural networks. Okay, so this is kind of the conclusion. So what I'm going to do next is maybe I had also meant to contrast this a bit with non-parametric methods, but since I'm a little short on time, maybe I'll skip ahead a little so I can tell you about overfitting. Sorry. Okay. So so any questions about robustness at this point? Okay. So in that case, what I'll do is I'll kind of move ahead to overfitting. So what do I mean by overfitting? Well, one of the things that has emerged lately is that deep generative models have been highly successful, right? So with GANs, we have managed to generate very realistic images, so realistic that, it's, deepfakes are literally, at this point, they are a serious concern. And they have been highly successful in a bunch of applications. But one of the questions that come up every so often is, do they overfit? Right. And before I get to this question of whether they overfit or not, let's try to understand what overfitting means. Okay. So, what would be an example of overfitting? Well, the kind of overfitting that we are looking at for the purpose of our work is when the generative model reproduces training data or reproduces small perturbations to the training data, right? So for example, if let's say your GAN generates you a face, well, is it just copying out a face that was there in the training data, right? And in some cases, in a lot of cases, in fact, this may be okay, right? Like if you are using it to generate, I don't know, if you're using it to generate, I guess, photos for like a movie or a project, I think this may be okay. But it could be also a concern in some cases, right? So for example, one of the cases that we were motivated by is, I also, as you know, I also work on privacy, and a lot and these days, one of the things that people are doing is for healthcare, data is very, very sensitive, right? So for healthcare, data is extremely sensitive. Nobody wants to release patient data. But one of the things that people are doing now is they are using GANs to generate synthetic patient data, right? Now, this is how you're using GANs, and if your GANs are really releasing real patients in your training data with very minor perturbations, that's an issue, right? Because like real people's data is being released, which does have privacy concerns, right? So there are cases where you this may not be true for all applications of GANs, but there are cases where you do care about whether your whether your generative model is outputting training data or small perturbations for the training data, and these are the kind of things we care about. Okay, so before I get to defining overfitting, let me start out with the setting and the classical view of overfitting. Okay, so here is the setting that we have. So we have some training data, which is used to build some kind of complicated generative model. And then what this model will be used to do is it will be used to generate some data, right? So, maybe you get a bunch of training data. Let's just say we are in a very, very, toy case. So you get a bunch of training data, you fit kind of a Gaussian to it, and then you just draw from that Gaussian. And so you have this generated data. And then you want to evaluate how good this generative model is. And so for that, what you have is access to another to some test data, which is data drawn IID from the same distribution. And using this training data, test data, and generated data, maybe you can get some score, right? You get some evaluation score, which tells you how good your generative model is, right? So this is our setting. And in the classical view, this is how we would detect overfitting, right? So what we would do is we would look at various models, and then we would measure their likelihood, or typically we would measure the log likelihood, but, let's just say we measure their likelihood. So their likelihood is the likelihood of the data given model, right? And typically, this is also what we would see, right? As we keep making our models more and more complex, it will keep fitting the training data better and better, right? So this red curve is the training likelihood, right? But after a while, what would happen is that if you look at how well it fits the test data, the test likelihood would go up, but then after a while it would start going down, right? And overfitting happens when there is this kind of large gap between the training likelihood and the test likelihood. So when that happens, that's when we say we have overfitting. Okay. So, oh, I see some questions in the chat. The question is, even in a case like the generative model reproducing photos, can one avoid the problem by choosing the input to the GAN as well, by taking an input that is a sum of inputs that created faces? I'm not sure I understand the question 100%.
Yeah, so I think this is from Game Cooper, and I just pinged there a separate challenge to try to get some clarification. So the idea is basically like, usually we sample images from a GAN by, picking some base samples and then passing them through the GAN, right? And so there's some distribution that we sample the base samples from. So the question is, can we change the distribution we sample the base samples from, or in some other way do something clever at the input side so that we're no longer generating samples that are close to the training data?
That is, that is plausible. I mean, we haven't experimented with that directly. Usually once we get to our experiments, you can see. So what we did is we just, picked this, in GANs, how you have this, you sample from the noise distribution and then you send it through the thing. That's how we did the experiments. But it's plausible that by choosing the initial point carefully, you may be able to avoid it. That's quite plausible.
Yeah, it seems like it would be interesting to see what happens if you sample from a different distribution that's not the original noise distribution you're trained on, but then you might lose a lot of other things. So
yeah, I actually don't know if somebody has done those experiments. I think they would be cool nevertheless, right? Yeah.
Thank you.
Yeah, that's a very good question. Yeah, I don't know. Oh, sorry, I don't know if somebody has done these experiments. Okay, there you go. Okay, so so then the next that's what would qualify for overfitting. However, this kind of test may be really hard to do for deep generative models. So one issue that might happen is that the likelihood may be really intractable. So for example, for VAEs, you can't really get the likelihood. You can just get an approximation to it, right? And the other issue is that for certain models like GANs, you don't really have the likelihood. You have only samples. And I mean, some people have talked about how to fit likelihoods to GANs, but it's but mostly what happens is that you don't really have likelihood, right? Like all you can do is you can draw a bunch of samples. And, these models have lots and lots of parameters. So we are talking about 10 to 100 millions of parameters. So overfitting might well be a concern, right? So this kind of thing might be happening. Maybe they memorize samples. We don't know, right? So what we will do today is we will start out by trying to formalize this kind of notion of overfitting. Okay. And in fact, what we did was when we looked at the literature, we realized that there were kind of two notions, somewhat orthogonal, of overfitting. Okay. And these two notions are what we will call overrepresentation and data copying. Okay. So what is overrepresentation? The overrepresentation means the following. Suppose you have your training data and generated data as well as test data. You say that there is overrepresentation in a particular region C if the fraction of generated data points from C is much, much greater than the fraction of either training data or test data in this region, right? To give you an example, if you look at the top square, there are 6 generated points versus 2 actual points from the distribution, right? So that would be an example, a case where overrepresentation is happening. The generated points are much more likely to come from this general region than training or test points, right? So that is overrepresentation. It turns out that there is another orthogonal type of overfitting that we call data copying, right? So what is data copying? Suppose you have your training data T, your generated data Q, and test data P, right? And suppose in addition that you have a distance metric D. You say that there is data copying in a region C if for generated data drawn from Q and test data drawn from P, on an average, the generated data are closer to their nearest training data point than test data, right? So what does this mean? So, imagine we took the case where what was happening is that the generative model was just spitting out, was just randomly subsampling some of the training data and spitting it out, right? Here, what would happen is that the distance between the generated points and their closest training point would be 0. Whereas if you took an independent test sample, of course, it won't be 0, right? Because an independent test sample, I mean, unless the data was completely supported on just those training distributions, in which case things are fine. But, there's those training points, an independent test sample, this distance would be more than 0, right? So this would be an example where you're data copying, right? So that would be an example of data copying, okay? So the thing to remember is that overrepresentation and data copying are somewhat orthogonal overfitting issues, right? So let me emphasize this by giving you an example. Suppose our underlying data distribution was, very, very simple. Let's say it was a mixture of 3 Gaussians with mixing weights 1/3 each, right? So 1/3, 1/3, 1/3, you have these 3 Gaussians, right? Suppose when suppose what your generative model did was that it picked out 2 of these Gaussians very accurately, but it completely ignored the third, right? So 50-50, let's say it picked out, Gaussians A and B 50-50 and completely forgot about C, right? If that happens, that is an example of overrepresentation, right? Because what is happening is, if you look at the region around each of these Gaussians, well, under the training distribution, this was, this would happen 1/3 of the time. And now, you get a sample from here half the time, right? So this is overrepresentation, right? In contrast, suppose you had the following case where, again, suppose your input distribution was a mixture of suppose your input distribution was a mixture of 3 Gaussians, 1/3, 1/3, 1/3. And what you did was you just, again, spit out just the training data, right? Here, you wouldn't really have overrepresentation. You spit out, let's just say, a bootstrap sample of the training data, right? You took the training data, you maybe picked out a random sample from there and spit it out, right? Let's say that's what our generative model is doing. It's just cheating, right? So if that was the case, you wouldn't have overrepresentation, right? Because if you took some region of space, well, the distribution is fine, right? Like your generated distribution is like the training distribution, very, very close to the training distribution. It's all fine. However, you do have data copying, because if you drew another independent test sample from the same distribution, well, those will not be lying on top of the training samples, right? So you do have data copying, but you don't have overrepresentation, right? So overrepresentation and data copying are fairly orthogonal. These are fairly orthogonal notions of overfitting. And so, I mean, as I'm sure many of you guys know, there's a lot of work on this kind of, measuring how well these generative models do. And there are many hypothesis tests on detecting, whether generative models are doing the right thing and testing for overfitting. And, these are just some examples from before our paper, but there's like many more since then. And, so anyway, so these are just some examples from before our paper. These are a bunch of existing hypothesis tests. And we went through all of them. And what we found, to our surprise, is that almost everybody, except for one exception, which I will talk about later when I talk about experiments, all of these tests, with one exception, they all test for overrepresentation, right? And almost all of them, except, 1 or 2 exceptions, they fail to detect even exact data copying, right? And, all of these tests, so what would happen is, even if you had generative models which cheated and just subsampled the training data and threw out a sample of the training data, they would perfectly pass these tests, and these tests will all be very happy. Okay, so this is kind of what we found. And so what we did after this was we went ahead to kind of propose a simple test of data copying. Okay. So what would a first test of data copying look like? So if you were trying to test for data copying, what is one of the first things that you would do, right? So the first kind of thing that comes to mind is you would go from the definition, right? So you have your metric, you have your test, training test and generated data. You would look at the average distance between the test data and the closest training point, and the average distance between the generated data and the closest training point. And if these two averages were really far apart, then what you would say is that sure, data copying is happening, right? However, the problem between these, and you can do statistical tests on this difference, right? If these differences if these two averages are far apart, you could do some statistical tests to see if, significant, if they're far apart with statistical significance, and, you do standard tests on that, then you're done, right? The problem with this sort of thing is that you can get pretty high variance from outliers, right? So if you have one or two outliers, they can really affect these tests quite a bit. Okay. So another solution is to use, instead of using directly the average of the distances, the other solution is to use comparisons, right? So what you do is you compare whether on an average, P is farther, P as in the test data is farther on an average to the closest training point. Our data points from P are farther on average to the closest training point than data points from Q. Right? And if you stare about this a little bit, I mean, it's not super obvious, but if you stare at this a little bit, what you find is that this reduces to a Mann-Whitney test on distances between P and their closest training, between points from P, the test points and their closest training points versus versus generated points and their closest training points, right? So this basically becomes a Mann-Whitney test. Okay, and and we know how to do them. Okay. Another issue arises when you look at deep generative models. So deep generative models are highly heterogeneous, right? Like these are huge models. We are looking at a very diverse set of data, right? Like if you think about, for example, like a big generative model, which is, let's just say, built on ImageNet, you have a whole bunch of different kinds of images, right? And the behavior of the model is also not the same everywhere, right? Like for certain parts of the space, it will behave one way, other parts it will behave in a different way. And so one of the problems that arises in this case is heterogeneity. So if you try to do a global test that, of this kind of, based on these kinds of distances, if you try to do a global test of data copying, then these global tests will fail for heterogeneous models, right? Because you can have one part of the space where the model is data copying and another part of the space where it's not, and then things can just kind of cancel out, right? So how do we account for them? And it turns out, there's in kind of the classical theory of non-parametric methods, people have done a fair bit of work looking at these sort of things. And what they do over there is use an algorithmic tool called binning. They divide the entire space into cells C, right? Then they do this kind of a data copying test in each of these cells, and then they report the weighted average of the one-sided test results. And if this average comes out to be significant, then what you can do is you can go inside each of these cells and see where things were positive, and that's kind of the region of the cell where data copying happened. Okay. So that was our test. Now let's look at what it does and how well it detects data copying. Okay. So I'm going to talk about, two kind of experiments. So one is when we looked at a VAE on MNIST, and the latent dimension went from 1, where it was underfitting, to 100, where it was overfitting, right? And, this is kind of known because, there's been some previous work by other groups. There's a group in Northeastern which showed that for 100, right, which didn't use our statistical test, but which showed that for 100, for a latent dimension 100 on MNIST, VAEs were really overfitting, right? And remember, our test also requires a metric, and the metric that we used was the 64-dimensional latent space of an autoencoder trained with a VGG-net perceptual loss, so which is one of the standard metrics that people use for, for MNIST, for example, measuring distance in the latent space for MNIST. Okay. And here is what we see. So what is happening is that the latent dimension is going from 100 to 0. So think about from overfitting to underfitting, right? And we are baselining with two others. So one is generalization gap, right? Generalization gap is the difference between the training and test likelihood that I mentioned. So notice that for VAU, you can't get the likelihood, but you can get something called elbows. So we are looking at the difference in the elbows, okay? Then our second baseline, looking for the difference in elbows. And if you look at, the picture for generalization gap, what you will see is that, the elbow is not very informative of this thing. It's probably because the elbow is not a very good approximation for likelihood. I don't know, right? But this is kind of what we see. The second baseline we have is something called the nearest neighbor test. And the nearest neighbor test, this is by Lopez Paz and Okwab in 2016. And this is a test where basically what they can do is they can detect exact data copying. They can probably detect exact data copying. But once things get to approximate data copying, then things get a little, things get a little iffy, right? So here also you can see, and by the way, this kind of 0.5 is kind of, where you're supposed to be for this kind of, for this nearest neighbor test. 0.5 is where you go from just sort of underfitting to data copying, right, to overfitting. So what is happening is that for the nearest neighbor test, it's always predicting that you are overfitting, right? Whereas if you look at our test, what you can see is there's kind of a continuous curve from underfitting to overfitting. So our test is supposed to be negative when you are underfitting, and it's supposed to go up when you are data copying. It's supposed to go up, and you see the smooth curve along which it happens. Okay. Our second case study that we did was on Big GAN, which is this huge GAN that has been trained on ImageNet by DeepMind. Now, my group, my group certainly does not have the computation power to train the Big GAN. So what we did was we took we took a pre-trained Big GAN, right? I mean, their pre-trained model is available. So we took the pre-trained Big GAN. And what we did was we did our tests on 3 ImageNet classes, Coffee, Bubble, and Schooner. So Coffee, I think 2 of these, I think Coffee and Bubble are, if you download the PyTorch code for Big GAN, then Coffee and Bubble are the 2 default classes, right? These are the 2 classes that they have, that they have demos on. So that's the 2 default classes. And then Schooner is another random class that my student Casey, who did the experiments, he randomly picked out. And it turns out, however, Big GAN has a parameter called the truncation threshold, which measures, in some sense, the diversity of the samples, right? So I think the truncation threshold is, for Michael, the truncation threshold is how you truncate the noise value that you put in, right? You put in a noise and then you get a generated sample. But the truncation threshold tells, if it's really, I believe if it's really small, then you just have a little bit of the distribution from which you are drawing that sample. Right? So it's measured by the truncation threshold. And the metric D that we took was the 64-dimensional PCA of the inception space. And this is kind of what we saw, right? So as you increase the truncation threshold, what you are doing is you are, so again, you are going from, so you're going from underfitting to overfitting, right? As you increase the truncation threshold, you're going from underfitting to overfitting. And as you can see, our test, the score of our statistical test kind of tracks this, right? Whereas we compared with this nearest neighbor test, there the things are more or less the same, right? You don't really see much of a difference as you keep increasing the truncation threshold. Whereas here you can see there is some difference. Our test scores go from underfitting to overfitting, right? And notice that because this is again, we couldn't get the generalization gap was not available because this is not a VAE, right? So this is our test. And just to give you some idea of what is really happening, this is, so we have two tables you can see. The first table is from a cell that our test reported as data copying, whereas the second table is from a cell that the test reported was not data copying. So here what we did is, by the way, we got to the cells by clustering the data points. So there were, I think, 3 or 4 clusters per class. Where we clustered the data points, and then each cluster was a cell, right? So here, if you look closely, what you can see is in both cells, among the real data, there is a lot of diversity in the coffee cups. So this is the coffee cup cell. This is the coffee cup class. So you can see in both real data, there's a lot of diversity among the coffee cups. But if you look at the data copied cell, what you can see is among the generated data, kind of the same coffee cup keeps showing up over and over again, right? There's one cup of espresso which looks kind of orangish brownish, and various views and various forms of it keeps showing up over and over again. So that is kind of what we are seeing over here. Okay. And in contrast, if you are looking at a cell where its things are not data copied, then what you see is, the samples are quite are reasonably diverse, right? So this is the difference. Okay. So what happened was, in conclusion, we presented a new 3-sample test for detecting data copying, and we also formalized 2 notions of overfitting. And sorry, so before I get to the references, and in some sense, in my mind, the real open question here is how do we measure generalization in deep generative models, right? This kind of likelihood difference is very hard to do in these cases, but are there different notions of generalization? What are the other notions of generalization in these deep generative models? Because these are really large and complex models, and it's unclear exactly how they're generalizing. So how can we measure? How can we prove properties? How can we prove properties of them? How can we measure what they're doing? How can we test if they're doing the right thing? And how can we even look into their failure modes, right? So to me, that is kind of the biggest open question that emerges from this work. And with that, let me, I will point you to the references. So these are kind of some of the work that we talked about. The first one is the work on neural networks and adversarial examples. And the last one is the work on the data copying. And here are all the people who did most of the work. So Cyrus was my postdoc, and he's now at Google. Yaoyan, Ishan, Roby, and Casey are my students. Shanja is, of course, a long-time collaborator, and Hongyang and Ruslan are our collaborators. And with that, I'll just stop and take your questions.
Thank you very much. Sorry, Adam had to hop off briefly, I think, to pick up his kids, but I will be a poor replacement for him. Do we have any questions from the audience or from the other panelists? Okay, well, we'll give people a chance to think. I've got a couple questions that I thought maybe we can chat about a little bit. So you mentioned kind of very briefly in the first part of the talk, this kind of smoothness versus generalization relationship, which exists in a particular way in classical theory and then seems to exist differently in deep learning theory, right? And I think we keep seeing these kinds of patterns, right? Where like, I mean, the sort of classical one is the whole kind of double descent line. And I'm sort of wondering if you can speculate a little bit about this, specifically whether, like, are we seeing another situation where we're just like out beyond the bounds of something that we know about and we're just in a new classical kind of new regime, or sorry, a new non-classical regime? Or is it the case that we haven't hit the classical regime yet with respect to this trade-off, and we're just like, our kind of algorithms are not even at the point yet where we're seeing this kind of classical behavior when it comes specifically to the smooth generalization question?
That is, I mean, that is a very, very good question. I really wish I knew what was going on, but my conjecture is the following. So my conjecture is that what is happening here is that there is a difference between in manifold smoothness and out of manifold smoothness, right? So here, when I talk about smoothness, and of course, for adversarial robustness also, right? When we talk about smoothness in the context of adversarial robustness, what we mean is smoothness out of the manifold as well. And what I think is happening is that somehow, at least in the way that we are ensuring smoothness out of the manifold, we are somehow taking away the generalization capacity inside the manifold.
I see.
I think that is what is happening over here. And by the way, let me also add in this context that a lot of, we have recently looked at a fair bit of deep learning theory. I'm not like, I don't directly work in this area, but we have recently looked at a fair bit of the theory in the hopes that some of it would explain adversarial examples, but we haven't found anything in the theoretical literature which does explain it. So, so this kind of thing that you have higher smoothness out of the manifold, but somehow it ruins things inside the manifold. So we haven't found any theory that explains it. So
well, that's a call to action to the
yes.
folks here for sure.
Yes.
Thank you. Does anybody else have kind of any additional questions? I mean, I'm going to go for one more while people are thinking. I noticed, like, for in the second part of the talk, you do have to pick a notion of distance to do any of this, right?
Right.
Do you have a sense of how sensitive the behavior is to what notion of distance you pick and what you actually use there? Because it seems like in the experiments, it's just like, and we pick this as a distance metric and it seems reasonable and everything works. Did you get lucky, or is this kind of invariant as long as your distance is reasonable?
So I think if you do it in the pixel space, then you wouldn't get anything too interesting unless you have a lot of data, right? So your distance has to be reasonably related to the perceptual distance. That's a good question. I mean, we haven't done experiments with a bunch of different distances, but my conjecture would be if it's one of these latent spaces, like if it's a reasonable latent space coming from a large model, so something that reasonably models perceptual distances, I think will be fine.
Cool. Yeah, thank you.